Hey everyone, we'll wait a few minutes for, a few seconds for people to get logged on, and then we'll get going. While we wait, I'll answer Bailey's question about whether I consider Pluto to be a planet. Good question. Lots of heated emotions about this. I'm pretty happy with the IAU's definition of a planet. If you're going to have a self-consistent definition of what a planet is, you either need to have Pluto not be a planet or be ready for the potential for not only a few or a few dozen or a few hundred, but potentially thousands of other things out there in the Kuiper Belt that are also planets. So I think it's a reasonable definition to make it so that Pluto is its own, the charter member of its own dwarf planet category. I think that makes perfect sense. But it's a semantic thing. Pluto's doing just fine out there. It doesn't really care what we call it. Okay, so welcome. We made it to Friday. That's exciting. I have not yet posted next week's homework assignment, but I will this afternoon. There will be a kappa on special relativity. You'll get to put some of these things we've been talking about into action. So that'll be fun. Next week's a normal week. I'll have office hours as normal. There's a kappa due at the usual time. It's just a normal week. Okay, I said that I would give the final verdict on how the final exam would work. And I'm ready to do that. So here we go. After talking to a couple people, here's what I decided to do. This is a more confusing way to do it, and it's much more complicated, but I think it's fairer to everyone. So let me tell you what I'm going to do. I'm going to calculate everybody's grade, and we're talking about the 60% or whatever of your grade that is specifically for the exams. I'm going to calculate that in two ways. One of them in the way that I already suggested, where you take the final exam, I take your middle two, I throw out the best and the worst score, I use the middle two scores to calculate an average, and I use that average. The other way I'm going to do it is to take all four exams and leave the three midterm exam, the first three exams as they are, but limit the fourth exam that you take to be in the range of your first three exams. In other words, if your fourth exam is higher than your highest exam you've had so far, I'll lower it down to be equal to the highest exam. If your exam score on that fourth exam is lower than the worst score you've ever had, I will raise it up to be equal to the worst score you've had on the first three exams. And I will, and that will give you four exam scores that I'll use to make an average. And then whichever of those two gives you the best grade, I will use that one. That make sense? I think that won't hurt anyone drastically and may even help some people in the end. So hopefully that will alleviate some anxiety, will make it so that last exam is still meaningful and still helpful and still worth studying for. But, you know, we'll take some of the anxiety away from, you know, whatever situation may be going on in your own situation. And also, you know, level the playing field for people who might not play fairly. So hopefully that will work. And that's my final answer. If you don't like it, that's okay. I apologize, but we have to go with something. And I wanted you to have at least a heads up before we got to that week on how it was actually gonna work. Okay, it still is the case in both of those situations that if you're happy with your first three scores, you don't really even have to take the final if you don't want to. A 0 will get bumped up to your lowest grade no matter what, or it will be ignored altogether if I take your top and bottom and throw them out. So either way we do it, you're welcome to not take the final exam if you'd like. So there you go. So if you have any questions, I will be happy to field them. So the way this is going to work, I will post your raw grade on Canvas. Canvas has no way to implement this crazy system. So your final grade in my grade book will not agree with whatever the final grade is on Canvas. And so I can maybe post that final grade in some not weird way, and maybe I'll do that. I'll figure out a way to post the final average as it is calculated in my grade book in some random other category that isn't actually counted for anything on Canvas, so that you can at least know what I got in my grade book. But hopefully that will be okay. Any questions?
So I'm just wondering, when is the final exam? Is it this next Friday?
It is not next Friday. It's not a week from today. It is 2 weeks from today, Friday, December 18th. So we have next week is a normal week of classes. Well, there'll be a Kappa on Thursday. We'll have class Monday, Wednesday, and Friday. There are 2 more Kappas. There'll be a second Kappa that will go up on the end of next week. That will be due the following Thursday, and then our final will be Friday. So I don't know at this point if the Wednesday before, so Wednesday the 16th, will be a class that is a normal class where we're actually covering content, or if I will have gotten through everything I need to cover, and we can just have that be a study day or a review session or whatever. So it may be that we've covered all the material that we need to either midway through Wednesday's class or before Wednesday's class, and whatever time we have left, we can devote to a review session or something. That make sense?
Yep, that makes sense. Oh, and also, so are we doing it where we just come in at some point during the day, or?
Yeah, so it's going to be, you know, I'll put the details up. I'll probably open it up at 8 in the morning on that Friday. I'll probably give you a full hour instead of 15 minutes or something, and you can choose whatever hour you want. And then you can take it anytime between 8 a.m., let's say, and sometime in the evening or night or whatever. I'll open it up, and it won't be synchronous. You can take it on your own. You'll start the exam, you'll upload the exam, and that'll be good. I'll probably actually give you like an hour and 10 minutes, and that will include the time that you need to, you know, take images of whatever work you've done and upload them, so that you've got plenty of time to do that. Make sense?
Yep, sounds good.
Okay, cool. Other questions? Okay, great. All right, where were we? Yeah, we were talking about some very weird stuff, weren't we? We're talking about how not only are different observers measuring different positions for events that occur in different places and times, but they measure different times for those events as well. And that's where special relativity gets very weird and very confusing. And many of the paradoxes that are seemingly paradoxes turn out not to be paradoxes at all when you understand that people aren't measuring time the same way. And it's very difficult to wrap your brain around this concept, and it takes, you know, probably 3 or 4 times seeing this before you might tend to get, hopefully you'll get it, but it may take a few times before you fully wrap your brain around what's happening here. So I think those metaphysics videos are important. I think they do a much better job than I can on a whiteboard of giving the overview of how this stuff works, and a beautiful visual of how this stuff works. So I will refer you to those as well. I posted a couple more for today. Hopefully you had a chance to look at them. Our goal, one of our goals for today, is to derive the Lorentz transformation. So the Lorentz transformation is that stretch squeezy rotation in the minute physics videos that you need in order to preserve the c being the speed of light in all reference frames. And so we need some algebraic expression to go from an x prime t prime coordinate to an x t coordinate, and that is the Lorentz transformation. So We can, without too much difficulty, actually derive that. So let's go ahead and do it. Okay, here we go. Lorentz transformation. So our goal here is to, yeah, exactly what I said. We want x as some function of x prime, and we want y as some function of y prime, et cetera, et cetera. T as some function of t prime, and t prime as some function of t. We want to be able to flip this as well. We want x prime as a function of x. This is our example. Okay, so let's say two moving coordinate systems agree on an event, right? So we've got two coordinate systems here. We've got some x, y, z. I'm going to actually draw the three spatial dimensions, so we actually have some reference frame of what's going on, and then some moving reference frame where you have some y, x prime, y prime, and z prime coordinate system, and these two coordinate systems are moving with respect to one another. This is the normal thing we've been doing up until now, except we've been ignoring the x, the y prime and the z prime, because it doesn't, nothing changes in those directions. It's only in the direction of motion that things get weird. Okay, so these two moving coordinate systems agree on an event. Usually you have to make this assumption at the beginning of all of these things. So let's say some flash bulb goes off at some point in space and some point in time. That is an event. So flash bulb goes off. And both observers will agree that that happens at the origin. So t equals t prime equals 0, and x equals x prime equals 0, x equals x prime equals 0. The other true too, y equals y prime equals 0, z equals z prime equals 0. That's what the origin means. It's these, so they agree on that particular event, and they're going to agree to set their origin to that particular event. Okay, so what is the path? So again, flash bulb goes off. Flash bulb means it's radiating outward in all directions. What is the shape of that expanding group of photons, light waves? What shape will that take as it expands?
Would it be spherical?
It will be a sphere, right? So in the non-moving frame, let's say this non-primed frame, it will be expanding out as a sphere. How about in the primed frame? What shape will it take?
Would it be something like an ellipse where like one side looks distorted?
You would think that, wouldn't you? But here's the thing. All observers in all reference frames have to observe this thing moving out at the speed of light in all directions. So believe it or not, it's also a perfectly symmetrically expanding sphere for the non-moving reference frame. In fact, there's nothing preferred about, there's nothing moving or not moving about either of these reference frames, right? From this perspective, this reference frame is moving to the right at some velocity. From the primed reference frame, this reference frame is just moving to the left at the same velocity, right? No one of those is preferred. So here is one of the first weird things. Both observers have to see again, there's no preferred orientation or location of that event, aside from the fact that they called it the origin. Both observers have to see the light bulb, the wavefront of that light flash bulb expanding in a perfectly symmetrical and spherical point about their own origin, even at time non equals 0. And that's weird, right? Because the origin points at t not equals 0 won't agree with each other in x anymore. And yet both observers have to see this flash bulb expanding at the speed of light. Okay, so where does that get us? It's weird, but where does that get us? We know what this looks like, right? We know how, remember, we've already drawn some of these diagrams. We've drawn Minkowski diagrams, right? So we have an X and a T axis, and we draw some speed of light thing here in the middle. And we know that if we have a moving observer, we get some different T prime frame. We'll call this CT just to make it a Minkowski diagram. And we also know, we derived yesterday, the fact that the X prime axis also has to move. And so you get something that looks like this for the X prime, where these two angles are exactly the same, right? But it's not just that these, as the Minute Physics video shows, it's not just that these axes shift. It's not just that things move. It's that they get stretched also. And so there's this squeeze stretch thing that happens. And so our job is to try to figure out what those how to quantify that squeeze stretch thing. Okay, well, the y and the z axes are simple, right? If you're moving with respect to the x-axis, then you can sort of just ignore them. Y and z are simple. Y equals y prime, z equals z prime. Since they're not moving in the y or z direction at all, you have no need to worry about anything going on in the y or z plane, which is why we're almost always doing this in the xt plane, because that's where interesting things are happening, not in the y or the z. I want to put them here so that you see that they're there, and if you want to think about them, you can, but nothing physically changes. If you're moving in the x direction, the y and the z axes are unchanged. Okay, so let's assume that, let's make one assumption. And that assumption is going to be that whatever stretch, squeeze, rotation we're going to do is linear, right? So in other words, it's not going to be bigger. You're not going to be stretching it more at large x and less at small x, or more at large t and less at small t. Let's assume it's the simplest thing we could do, and it turns out to be right, that this is a linear stretch. It's a much simpler thing to think about. So that's the only assumption we're going to make in doing this derivation. So what does having that linear, what does making that assumption linear mean? We know that, all right, so we already had y equals y prime, we had z equals z prime. You might remember that we wrote down a naive version for what x prime was as a function of x. And we found, remember, this is the very first lecture where we're talking about coordinate transformations. If in the naive, non-relativistic assumption, this was just x prime equals x minus vt, right? If you just have a very small velocity, this is what you would expect the x prime, how x prime and x would be related. However, those reference frames are moving with respect to each other with v, the more further away in time you get, the further away these two coordinates are going to get. This is Galilean. This is the non-relativistic Galilean. So we know that this would be true of Galilean. We know that in relativistic terms it's not true. We also know that the Galilean, these are both Galilean, t prime would equal t, and we know that that's not true anymore. Okay, so what does it mean? So what is assuming a linear relationship between these mean? Basically, it means that instead of x prime equaling x minus vt, x prime must be equal to x minus vt times some linear constant, times some linear offset. Let's call that a linear offset gamma. And gamma cannot depend on x or t, because if gamma depends on x or t, then this is no longer a linear equation, right? This has to be some constant. It can be related to something else. It can't be related to x or t, because that's our coordinate system. It can be related to v, as we'll see. It also must be true. What must be true of gamma if v is much less than c? What must gamma be as v goes to 0, say?
1, right?
It has to be 1, right? If velocity is much less than c, then we have to revert back to the Galilean transformation, right? So gamma must be something such that if v is much less than c, then gamma is basically 1. So whatever we get has to have that property as well. Here's something else. It must work in reverse. In other words, whatever transformation we do to transform x prime into x, we also have to be able to transform x into x prime. So we have to be able to do this in both directions. What does that mean? It means that xx must be equal to, let's say, some gamma prime times x prime minus vt prime, right? This must also be true. Oh, I'm sorry, and it's not minus here, it's plus, because we are assuming that the prime frame is moving in the positive x direction with respect to the unprimed frame, and that gives you a negative sign here. That the opposite has to be true. You have to get a plus sign here if you're going in the opposite direction. So this sign is the opposite of the direction that this frame is moving in with respect to the other one. Okay, so also we need the laws of physics to be the same in all moving reference frames. So it also must be the case that gamma can't be different than transforming one direction to the other. So these two have to be the same. It has to be a single parameter that defines this transformation. Otherwise, if you transformed there and then back, you wouldn't get back to the place you started from, and you have to. So these gammas have to be the same. Okay, so I'll just replace this prime here altogether, and these both must be true. Okay, so what is the wavefront of the expanding flash on the x-axis? We know that it's moving out in a spherically symmetric sense, but if we just look at the plus x axis, we're just noticing that wavefront moving linearly to the right as a function of time. So the x position of that wavefront is simply equal to how fast it's moving, the speed of light, times the time it takes to get there. That is the location of that wavefront over time. And it also must be the case that the primed observer sees that exact same thing. The speed of light must be exactly the same for that prime observer, and therefore it must also be true that x prime, the location of that flash in the primed frame, is just equal to c times t prime. This is due to the fact that both observers have to see the wavefront expanding at the speed of light. This is the location of the flash as it expands out. Okay, now it's algebra. I think we've got everything we need. We just need to put some algebra in here. Let's see if I can, with my limited board space, figure this out. Okay, so let's start with this one. X prime equals CT prime, but CT prime, or X prime, must also equal this thing. So let's plug this in. That must equal gamma times x minus vt. So let's right. So x, though, is CT. So let's plug in CT for x. This is gamma times CT minus VT. Now, this is again, the x prime location of the expanding flash point. We can pull a t out. This becomes gamma t times c minus v. We can now, so CT prime is equal to this. We can divide both sides by c, and we get t prime equals gamma t over c times c minus v. And if we pull the c into the parentheses, this just becomes gamma t times 1 minus v over c. So now we have a relationship between t and t prime in terms of this gamma function and in terms of v over c. What's our goal? Our goal is to figure out what this gamma thing is. And we need to remove all of the t's and x's primes and t primes. We want to get gamma just in terms of v and c, because it's got to be related to v and c. Okay, that's our goal. So we're not quite there yet, but we can do this exact same thing in the opposite direction. So let's start with x. We know that x equals ct. I'm going to do exactly the same thing. This is gamma times x prime plus vt prime. The only difference is there's a plus here instead of a minus. This is, again, plug it in x prime for ct prime. This is gamma times ct prime. I'm doing exactly the same thing, but in the opposite sense. Vt prime. We can pull out a c. We get t equals gamma times t prime over c times c plus v. And finally, gamma t times 1 plus v over c. We get exactly the same thing going another direction. We've got t prime equals gamma t times 1 minus vc. And t, oh, I forgot the prime here somewhere. These are all primes. That's a prime. Missed that one. So two symmetric equations relating t prime and t prime, with the difference that we've got a minus on the top one and a plus on the bottom. Great. So now we can, let's call this equation 1 and equation 2. We can plug this equation for t into this equation. So we're going to take this and plug it in there for that t. And let's see what we get. 2 into 1. We get t prime equals gamma times gamma t prime. Well, let's keep this. This t becomes gamma t prime times 1 plus v over c times 1 minus v over c. Okay, this becomes gamma squared t prime, and I get a 1 plus v over c times a 1 minus v over c, and I can simplify that to a 1 minus v squared over c squared, taking these two and combining them together into one term. And that's t prime. And now I can divide both sides by t prime. The t primes actually go away. And this is what my goal was, to get rid of the t's and the x's and the t primes and the x primes. And we've done it now. And we get 1 equals gamma squared times 1 minus v squared over c squared. And that's basically, we're there. We can solve now for gamma as a function of v and c. So gamma squared must be equal to 1 over 1 minus v squared over c squared. And therefore, gamma must be 1 over the square root of 1 minus v squared over c squared. We'll make a definition. V over c is going to become an important parameter for everything that we do moving forward. It's worthy of its own symbol. And the symbol that we give it, we define beta to be defined to be v over c. It's the fraction of the speed of light that your reference frames are moving with respect to one another. So this can be rewritten 1 over the square root of 1 minus beta squared. Cool. That's it. That's the Lorentz transformation. We know what gamma is now. We have defined that is how you go about doing this. So this implies that x prime equals gamma times x minus vt, or if you like, x minus vt since we know what gamma is now, square root of 1 minus beta squared. And that deserves a box. We also know that we can do this in the opposite direction. If we want to go from x to x prime. The only difference is you have a plus here instead of a minus because they're moving in opposite directions. 1 minus beta squared. And that deserves also a, so again, what assumptions have we made here? This is for the x prime moving in the plus x direction with respect to the unprimed frame, right? If they are moving in the opposite directions, then these signs switch. This becomes a positive and that becomes a negative. But there's no real reason to do that, right? You should always define your primed frame to be the one that's moving in the positive x direction. Or if you like, you should define the positive x direction to be the direction that the prime frame is moving in. You always have the freedom to do that. So there's no reason really to mess with these plus and minus signs at all. What about time? How does t and t prime, how does t relate to t prime and how does t prime relate to t? The book goes over this derivation as well. I don't think there's much to be gained about doing more algebra. It's a little messier and the insights aren't really there. The basic concept is the same though. You can use the same arguments and the same kind of logic to show that t prime equals t minus vx over c squared divided by square root of 1 minus beta squared. Or usually this is done ct prime instead. Multiply both sides by c because this is again usually our x-axis. Usually our y-axis is going to be the ct prime frame and not just the t prime frame. You're often thinking about this in terms of ct instead of just t. And then you can just multiply both sides by c. You get ct minus v over c. Actually, one of these c's go away. So this just becomes beta x divided by the square root of 1 minus beta squared. That deserves a box. And if you want to go in the opposite direction, you can. Ct is equal to ct prime. Again, all you have to do is change the sign in the numerator. So that's it. That's the Lorentz transformation. This is the mathematical tools to do the stretch squeeze thing that they talked about in the minute physics video. It's unusual. It's kind of confusing. The hard part about this is knowing what the prime frame is and the unprimed frame is and keeping all of that straight. It can get very confusing. But the equations themselves, and the equations are a little bit messy, but it's not that tricky, right? This is a pretty simple, straightforward. If you have an x prime and a t prime coordinate, and you'll have this on some of your problems for next week's kappa, you can use these equations to get to go from a prime frame to an unprimed frame, or back, and back again, wherever you are. So these are the useful Lorentz transformations. Okay, do they have the right limits? This is obviously an important thing. Let's see. As v over c goes to 0, or as v goes to 0, beta goes to 0, right? This is basically v over c. So as beta goes to 0, 1 minus beta squared goes to 1. Square root of 1 minus beta squared goes to 1. This goes to 1. And you've got x prime equals x minus vt. That's what you want. As beta squared goes to 1, or as beta goes to 0, beta squared goes to 0. This 1 minus 0 is 1. This goes away, and we're back in the Galilean regime, which is what we need. This is a little more confusing, but it actually works pretty well. As beta goes to 0, this term goes to 0, and this term goes to 1, and we get ct prime equals t, which is exactly what we want. And same thing over here. Beta goes to 0, this term goes to 0, this term goes to 1. We get ct equals ct prime. So it has the right limits. In the limit that beta goes to 0, we recover the Galilean transformations the naive assumptions that you would make if you weren't considering special relativity. Okay, so we really only need to worry if V over C is, not 0. Where do we have to think about making, how fast do you have to be going before you have to start making these corrections? Well, obviously it depends on how accurate you want to be. But let's say for practical purposes, let's do a calculation. What if beta were 1? Or not beta 1. Beta 1 is the speed of light. You can't go beta 1. Let's say beta is 0.1. I can erase this transformation now. Here we go. For beta equals 0.1. Well, beta squared, therefore, 0.1 squared is 0.01. Right? So 1 minus beta squared is 1 minus 0.01 is 0.99. The square root of 1 minus beta squared is about 0.995. 1 over 1 minus square root of 1 minus beta squared is 1 over this thing. You get about 1.005, right? So this is gamma, right? This is sort of the term that we're going to be using to characterize how much things are changing. And so if you're moving 10% the speed of light, this is about a 0.5% effect, right? Gamma equals 1 is the non-relativistic case. Gamma, I didn't mention this, but this is important. Gamma, beta has to be between 0 and 1. I suppose if you want to consider light moving in the negative x direction, it could go between -1 and 1. Beta cannot be bigger than 1 because nothing can go faster than the speed of light in an absolute sense. So beta must be less than 1. Gamma has to be greater than 1. Always. Right? For any beta between 0 and 1, gamma will always be greater than 1 for the same reasons we're seeing here, right? You're taking 1 minus it, taking the square root, and you're taking it inverse. And so whatever you get, number that's going to be less than 1 for 1 minus beta squared, you're going to get something greater than 1 for gamma. So this is just something to have in mind. Again, you need to have, an idea of what to expect. If you calculate a gamma that's 0.5, you've done something wrong. If you calculate a beta that's 1.5, you've done something wrong. You need to know what domains each of these parameters is allowed to be on. And for beta, it's between -1 and 1 maybe. But for gamma, it is always greater than 1. It can be equal to 1, I suppose, if velocity is 0. But that's the unexciting case. For non-zero velocity moving reference frames, gamma will always be greater than 1. Okay. Great. So again, for 10% the speed of light, you're only getting stretch, squeeze, stretch scale factors by about 0.5%, right? What is the limit as V goes to C? Obviously, as V goes to C, beta goes to 1. 1 minus beta squared goes to 0. Square root of 1 minus beta squared goes to 0. And gamma, which is 1 over the square root of 1 minus beta squared, this thing's going to 0. This thing has to go to infinity. Gamma blows up. So as beta gets closer and closer to 1, gamma gets large very, very quickly. This is another reason why you can't go faster than the speed of light. This gamma term will become infinitely stretched and beyond infinitely stretched. Okay. We've got 10 minutes left. Let's start to think about time dilation and length contraction, and actually putting some numbers where our thought experiments were before. Let's go back to our train experiment. You might remember on our train, we shined a laser, and we were interested, this is just a thought experiment to show that these two observers can't be measuring time the same. Laser bounces off the ceiling and then returns, right? So this is on the train, the observer on the train, observing this phenomenon. This is a fairly straightforward thing to calculate. The total time that it takes, let's call this the primed frame because this is actually going to be moving to our right compared to the observer on the platform, is just some delta x I call this delta x, but it really isn't x. It's really delta y because this is the x direction and this is going to be the y direction. So it's delta y prime, basically how far it's moved divided by this, how fast it's moving. This is just velocity, time equals distance divided by velocity. We know, let's call this distance h, the height of our train. So it's made the round trip. Its total delta y is 2h, and its speed is c, right? So somebody on the train, this is an analyte 1 problem to figure out how long it's taken them to get for that laser to bounce off the ceiling and come back. Okay, for an observer on the ground, something different is happening. For an observer on the ground, we see this laser start here, reach some point up here, bounce off a mirror, and then return back to this point here, right? Now, what is true of this distance? That's in the y direction. Y is equal to y prime. There shouldn't, these two observers will agree on what that distance is because that is perpendicular to the direction of motion, right? What is, so we've got, what is this distance? That distance is going to depend on how fast that train is moving. It's going to depend on the velocity of the primed frame with respect to the unprimed frame, right? This whole thing, let me actually put this ground up here so it's not in our way. This whole thing has to be the velocity of the train times delta t, the time it takes this whole thing to bounce up and down, right? That's how far the train has moved in time delta t. Its velocity times whatever that delta t was. All right, how about how about this distance here? Right, this distance is going to be, again, if you have delta t, you know that that distance is going to be half of the time that it takes light to travel this whole path, right? And the time that it takes light to travel that whole path is c times delta t, right? This is the speed of light times however long it took that distance to take. Now we know that this particular loop is going to be c delta t over 2. And if we want to consider this right triangle, that piece of it is v delta t over 2. So we've got some right triangle here that we can use to make some interesting arguments about what's going on. We know that the hypotenuse of this triangle squared, c delta t over 2, quantity squared, must be equal to h squared plus this side squared, v delta t over 2 squared. Okay, let's expand these squares and bring this term over here. We get c squared delta t squared over 4 minus v squared delta t squared over 4 equals h squared. Let's pull a delta t squared over 4 out of this. We get delta t squared over 4 times c squared minus b squared is equal to h squared. And we can solve this for delta t now. Delta t equals, we've taken the square root, so this becomes 2h divided by the square root of c squared minus v squared. And this is equal to 2h over c times 1 over the square root of, pulling a c out of here and making this a v over c. Apparently people like to do that. 1 minus v squared over c squared. And look, this is what?
Gamma.
That's gamma. That's exactly gamma. Delta t is 2h over c times gamma. And what's 2h over c?
That's delta t prime.
That's delta t prime. So this gamma thing tells us how much differently time is running for the person on the train as opposed to the person on the platform. They are different by a factor of gamma. What is this? Is it larger or smaller? So in other words, is the is this delta t larger or smaller than this delta t prime?
Delta t has to be larger than delta t prime because gamma is always bigger than 1.
Exactly. Gamma is always bigger than 1. So delta t prime is always large. Delta t is always larger than delta t prime. What does that imply? What is it? So you can calculate it now, right? Just multiply by a gamma. But what does it physically mean? An observer on the ground, more time will have elapsed than an observer on the train. And you know now exactly how much more time based on how fast that train is moving by. An observer on the ground will see the clocks on the train moving slower. They have to. So that's very weird. And this isn't, again, any sort of time travel thing or time, light travel time thing. This is a, fundamental difference in the way they're observing time. Now, what must be true? What will someone on the train see? This is where it gets really weird. So let's say there's a nice big clock on the platform and somebody on the train goes by. Will somebody on the train see that clock moving faster, therefore?
No, they also see it moving slower because it's just moving in the negative x direction.
Yeah, you could do this experiment in reverse, right? Instead of having the laser on the train, let's put the laser on the platform. It must, you get exactly the same thing in the opposite sense. Somebody on the train must also be seeing the platform's clocks moving slower. That's where some of this weird stuff starts to really kick in, right? We must see the clocks on a moving train moving slower than us, but the person on the train sees our clocks moving slower also. How is it possible that we can both see each other's clocks moving slowly? I will, it's a great question to ponder over the weekend. And I'm not gonna, well, I can't answer it in 1 minute anyway, so I'm not gonna try. But that's the thing, that's the weirdness of what this is. Many of the paradoxes that you hear about and we'll talk about arise from an incomplete understanding of how that phenomenon actually works. So we will come back next week and talk about some of those paradoxes and do some more calculations and think about not only time dilation, but length contraction also. And I encourage you to watch those minute physics videos if you have not already. We'll watch some other videos at the beginning of next week also in class. I hope you have an excellent weekend and we will pick it up again on Monday. Bye, everyone.
Thank you.
Thank you. Nice weekend.
Bye-bye.
Bye.